So it says a swallow is a type of bird. There's several varieties of swallow. In an experiment using 5 European swallows and 5 African swallows, they somehow measure the maximum weight that each bird can carry. And so X is going to be, X and Y are the heaviest weight that the bird is capable of carrying for the 5 European swallows and the 5 African swallows. Your hypothesis, you're claiming that the population mean of the African swallows is going to be greater than the population mean of the European swallows. So you're just saying in general, I think an African swallow can carry more weight than a European swallow. And the question is there any evidence in favor of your hypothesis? Well, we should start off by trying to approximate our population mean of each species by calculating our sample means. And gotta grab our calculator, go to Stat, Edit, and in list 1 I'm going to put 5.8, 4.9. Oh. It'll be faster if I do it from here. .1, 5.6, and 5.9. And in list 2, I'm going to put 5.8, 7.6, 5.6, 5.5, 4.9. Okay. So I have that data in my list 1 and list 2. Then we go to Stat, we go to Calculate, we go to one variable statistics. And for list 1, where I put my X values, that mean was 5.46. 5.46. And for my second group, maybe I have to go to 2 variable statistics. I know you can change the list in one variable statistics, but if you're lazy, this works just as well. And it says Y bar is 5.88. So sure enough, at least the sample mean for the African swallows is higher than the sample mean for the European swallows. So there is some evidence. Whenever you ask the question, is there any evidence at all? Well, yeah, based on the data I've collected, there is some evidence because at least my sample mean for the African swallows was greater than the sample mean for the European swallows. How much evidence does this represent? We don't really know. That's the point of our hypothesis test. So what I'm comparing right now is 2 population means. And is this type of data, is this going to be dependent or independent data, would you say?
Independent?
Yep. This is going to be independent because these birds aren't associated with each other pairwise in any way, right? These are just random samples from 2 different populations. So these are going to be independent. And in my TI-84, I'm going to go to Stat and then over to Tests. And so I'm looking at a 2-sample t-test, I think, because I'm going to use the t-distribution. I'm using the t-distribution because I can calculate a sample standard deviation, but I don't exactly precisely know the population standard deviation, hence the t-test for the t-distribution. And of course, I'm dealing with 2 samples here. And independent data, so I use number 4. I leave list 1 and list 2 alone. I leave the frequencies at 1. My hypothesis here is that the population mean for group 2 should be greater than the population mean for group 1. In other words, African swallows can carry more than European. So I want mu1 to be less than mu2, and so I've actually selected the correct thing already here. Pooled is always no. I wonder if you can choose a color besides blue. Oh, you can make it dark gray or red. Okay, so that's up to you, and then you can click draw and see what happens. And remember that the area under this little t distribution curve represents the p-value, and the p-value is the probability of making a type 1 error if you conclude in favor of your hypothesis. Like, if you go around claiming that you were right, your hypothesis was correct, your p-value, in this case 22%, that's the probability that you're actually wrong and that you're making a type 1 error. So how confident should you be? That would be 1 minus your p-value. And so that's 1 minus 0.22, which is 0.78 or 78%. You should be 78% confident that African swallows can carry more weight than European swallows. What would be the probability that you're wrong? Well, there's actually a 22% probability that you're wrong. That's a pretty big probability that your hypothesis is actually not correct. So, in my opinion, if there's a 22% probability that I'm wrong about something, I probably don't publish my work. I probably just try to collect more data maybe, or just give up, depending on what kind of claim it is. Questions about this? Hypothesis test regarding 2 population means. Okay. Question 2 says, in an upcoming political election, Mr. Red is running against Miss Blue. A political commentator on TV claims that, and this is the claim, a higher proportion of voters in Houston are going to vote for Miss Blue than in Dallas. So in both Houston and Dallas, some voters are going to vote for Mr. Red, some voters are going to vote for Miss Blue. We're going to talk about the proportion of voters that vote for Miss Blue in both Houston and Dallas. And the TV commentator is making the claim that that proportion is going to be higher in Houston. So let me just write this out in a way that makes sense to me. In Houston, we're going to call this population number 1, and I'm going to say that my sample proportion is going to be x1 over n1. So n1 is going to be my sample size. How many voters in Houston am I looking at? x1 is going to be the number of those voters that is voting for Miss Blue. Then in Dallas, we have another population of voters, called population number 2, and we could calculate a sample proportion if I go to Dallas and I take a sample of n2 voters, and I find that x2 of them, that's going to be my number that are voting for Miss Blue, and so I can calculate these sample proportions. But my hypothesis, the claim I'm trying to support, what I'm trying to seek evidence for, this is my alternative hypothesis, that's going to be that the proportion of voters in Houston is going to be higher than the proportion of voters in Dallas, where I'm not putting a p hat on it because my claim is about the population proportion. So my null hypothesis would be just the converse of this. And so whenever you see this p naught show up in formulas, that's going to be, oops, nope, never mind. Sorry, thinking about a one proportion thing. Okay. What we really care about today is what the heck is our alternative hypothesis? What am I seeking evidence for? Okay, and we're asking, is there any evidence at all? Well, let me calculate my sample proportions. In Houston, we surveyed 50 residents. In Dallas, we surveyed 30 residents. In Houston, 31 said they planned on voting for Miss Blue, but in Dallas, 16. Oh, no, I have to read more carefully. In Dallas, 16 tell you they plan to vote for Mr. Red. So how many plan to vote for Miss Blue in Dallas? That would be 14. Yeah, okay. We're assuming this is a two-party system, I guess. No one's voting for the independents. All right. So we have our sample proportions, and P1 hat is going to be 0.62. P2 hat is going to be something like 0.43, 0.44. What do you get? .46?
0.47.
0.47, okay. It's getting closer and closer. And anyways, the question is, does this represent any evidence of my alternative hypothesis? And sure enough, yeah, my sample proportions actually do show me that P1 hat is greater than P2 hat, so that's some evidence for my claim. How much evidence is it? So we're asking how much confidence should we have in our claim? And I will need my calculator. So I choose stat. Let's go over to tests. And what kind of hypothesis is this? We're comparing two population proportions. And with proportions, we're going to use the z-test, because we can theoretically determine exactly the population standard deviation using square root of p times 1 minus p over n. So that's going to be a z-test, not a t-test. And in this case, we're dealing with two proportions, so I think number 6 is the right choice. Then x1 is going to be 31. n1 was 50. x2 is going to be 14. n2 is 30. My alternative hypothesis says P1 is greater than P2. So P1 greater than P2, it's that choice on the right. Let's make it green this time. Maybe pick draw. So that curve now is the standard normal distribution curve, PDF curve. Areas under the curve represent probabilities, and this shaded area represents our p-value. That's the probability of making a type 1 error if you conclude in favor of your hypothesis. So if we claim that our hypothesis is true, my p-value is 0.09, so there would be a 9% chance that we were wrong. And so if there's a 9% chance you're wrong, that means you should be about 91% confident. And hence, there's a 9% chance that you're wrong if you go around claiming this on TV. So no one's ever perfectly sure. You think, yeah, that's a lot of evidence, in favor of saying that the proportion in Houston will be larger than the proportion in Dallas, and yet there's still a 9% chance based on that survey that that's not actually correct. And so people get really, people get really mad, I think, around elections, because there's a group called, what is it called? It's a number. It's like 528. How many electoral college votes are there? You know what I'm talking about? What's the group that predicts the outcome of elections? Group that predicts outcome of elections. It's called... Is it 538? Yeah, it is 538. Okay. So there's this website called 538, and I think it's named that because there's like 538 electoral votes. And the way that this works is that every single time that there is a survey done prior to a presidential election, they put that data into like a really big, what do you call it? A really big database of, just like statistical survey data. And statisticians who are much better than me at statistics, who actually do that as their professional job, they calculate things like these hypothesis tests, right? But in a little bit more sophisticated manner that we're not going to learn in this class. And they use these sort of hypothesis tests to make claims before the election about who they think is going to win, but they always tell you their degree of confidence, right? So in this case, they run simulations, and they said, well, prior to the election, I guess, they determined that there was going to be a 10% chance that Trump wins and an 89% chance that Biden was going to win the election. And again, they're not 100% certain that one or the other is going to win the election because it hasn't happened yet. So they have to always report their level of confidence and the probability that they might be wrong. Well, a lot of times, cable TV or even just regular network TV, they will say, oh yeah, we're predicting so-and-so is going to win the election. And then when they're wrong, people get really mad, right? Like in the 2016 election, 538 was projecting Hillary Clinton to win the election, and when Donald Trump won, a lot of people were really upset. They were like, what's the deal? I thought Hillary Clinton was supposed to win this election. Well, again, this is based on survey data, and with survey data, even when you do a proper statistical hypothesis test, that only tells you probabilities, and there's always some probability that you're going to be wrong about a prediction you're making on survey data, right? So you might think, I can't believe that they were wrong because they said they had 95% confidence, right? But even with 95% confidence, 1 in every 20 elections is going to be wrong. So, you can't take anything for certain. All right, question 3 says, Proactive is a pharmaceutical company that makes acne treatment products. They have developed a new face cream that's intended to reduce the incidence of acne on the face of teenagers. To test the effectiveness of their product, they recruit a cohort of 10 teenagers. And so there's 1, 2, 3, 4, 5, 6, 7, 8. Oops. 9 teenagers. For every teenager, they assign half of their face to be treated with the new acne cream product, and the other half is going to be treated with an unmedicated lotion. And this would ideally be double blind, where they label the creams, but they don't tell the participants which one is actually the acne cream and which one's the lotion. And at the end of a 30-day period, they're going to count the number of pimples on each side of the participant's face and then aggregate it below on this table. So each row represents one participant, and each participant has an untreated side and a treated side of their face. Is this data going to be what we call independent data or dependent data? This is dependent data because it comes from a matched pairs design. If you have a matched pairs experiment design, then you're talking about dependent data. So obviously the matched pairs are the two sides of somebody's face. And the way that we deal with this in our hypothesis test is we say, well, my method here is I'm going to calculate differences. And my difference is just going to be the untreated minus the treated. So 5 minus 5, 0. 5 minus 6, -1. 7 minus 2, 5. 6 minus 3, 3. 10 minus 7, 3. 11 minus 1, 10. 4, 5, and 9, let's say. So I'm counting the difference now. And my alternative hypothesis, my claim here, is that the untreated side of their face should have more, acne pimples than the treated side of their face if our product is effective. And the way I've calculated my difference as untreated minus treated, that means my alternative hypothesis is that this difference is greater than 0. And specifically, I mean the population mean of that difference is greater than 0. Well, so I can't calculate the population mean because I haven't perform this experiment on the entire population, but I can calculate a sample mean. So I'm going to use d bar to represent my sample mean, and to get a good sample mean, I need to go to stat, edit, and I have 0, -1, 5, 3, 3, 10, 4, 5, 9. And then I go to stat. We're going to go over to one variable statistics. Go down to calculate. And my sample mean is 3.2. And so when I'm asked the question, is there any evidence at all that this cream is effective? I would say, yeah, there's some evidence. I don't know how much yet, but I just know that based on my little cohort of experiment participants, my group of 9 subjects, that there does seem to be an average positive difference happening to each side of their face. The last question asks, well, second to last question, how much confidence should we have, right? So that's the whole point of a hypothesis test, is to determine that probability. We are comparing 2 population means, but since our data is dependent, we're actually just going to use the plain old number 2 t-test. We're using a t-test, we're using the t-distribution because we're not exactly sure what the population standard deviation is. We can calculate a sample standard deviation, but we don't know what the population standard deviation is, so we're using a t-test, and I'm only going to use the t-test and not the 2-sample t-test because, again, I'm looking at my differences since this is dependent data. So my mu naught is going to be 0 in this case. I've already got my data in my list. Frequency is 1. My hypothesis is that my population mean is greater than 0, so I'll say my population mean is greater than mu naught, since I told my calculator mu naught would be 0. Let's make this orange and then draw it. So I don't even see the shaded region because my p-value is so small. Again, that curve represents the t-distribution probability density function, so any area under the curve represents a probability. And it turns out the probability of making a type 1 error is so small we don't even really see it. I guess it's out here to the right somewhere. So the p-value is 0.006. And my confidence is going to be 1 minus my p-value. So my confidence is like 99.4%. And that means there's a 0.6% chance that you are actually falsely advertising, right, based on the survey results. So that's a pretty high degree of confidence. And what that's saying is you're just 99.4% sure that after seeing these results, seeing how most of the participants have a pretty significant decrease in their number of pimples from one side to the other, gives you pretty good confidence that if you applied this acne treatment cream to every teenager in the United States, you would see a decrease in the population mean number of pimples in the United States, right? That's a pretty easy claim to come to based on the evidence, so you have a 99.4% confidence. Okay, last question. Not Active is another pharmaceutical company that makes gout treatment pills. I tell you the story about the guy, never mind. I'll tell you when I'm not recording the video. They have developed a new pill intended to reduce the severity of gout. To test the effectiveness of their product, they recruit a cohort of 5 pairs of identical twins. So we have 1, 2, 3. Okay, we actually have 5 pairs this time. And all of them suffer from gout. All 10 of our participants say they suffer from gout. And for every pair of twins, they're going to assign one to be treated with a new pill and the other one to just receive a placebo, like a sugar pill that would be the same size and shape. They wouldn't know the difference. They wouldn't know which one they're receiving. But at the end of a 7-day period, they're going to ask each participant to rate their level of gout pain. And so the data is presented below. Is this data dependent or independent?
Dependent?
Yep, it's dependent because this is a matched pairs design. Specifically, we're matching up pairs of identical twins as our subjects here. So dependent data. What I'm going to do for dependent data is I'm going to look at the differences. So I'll just look at untreated minus treated. So 6 minus 5 is 1, 5 minus 8 is negative 3, 6 minus 7 is negative 1, 5 minus 4 is 1, 7 minus 6 is 1. And to average this, you just add those up and divide by 5, right? So adding them up looks like negative 4 plus 3 is negative 1. So my sample mean is going to be negative 1/5. What would my alternative hypothesis be? What am I trying to find evidence for? Well, if I'm trying to actually sell this pill, and selling it implies that I'm convincing people that it really does reduce the severity of gout pain, well, then my claim that I'm seeking evidence for is that the population mean of this difference should be greater than 0. You want to see the untreated participants have more severe gout pain than the participants that were treated with your product, right? So is there any evidence at all that this pill is effective? No, because this sample statistic it actually disagrees with the claim that I'm trying to make. So this data I've collected does not do me any favors for trying to convince anybody that this treatment works, right? So no. Maybe if you collected more data, you could try again, but in this case, with this sample, there's really no evidence that this pill is effective. It seems more likely that the null hypothesis would be true. It seems more likely that this difference is less than or equal to 0. Okay, so if you're the statistician, you don't get to make all the decisions in the company. You have managers that you work for. And if you tell the managers that, hey, there's really no evidence that our pill is effective, there is a such thing called fraud. So maybe your manager goes out and claims this anyways, even with a lack of evidence. So in that case, how much confidence would you say that you have that this pill is effective? Let's go ahead and try to do a hypothesis test anyways and just see what happens. So we're talking about a t-test. Is what we use for dependent data. So number 2, I'm going to click stats because, no, I'm not. I'm too lazy to calculate a standard deviation. So I'm going to go to stats. I'm going to go to edit, and I'm going to replace my list with my differences, which is 1, -3, -1, 1, and 1. Okay. Now we're going back to test. Back to t-test. I'm not going to choose stats. I'm going to choose data so that it will calculate that for me. Mu naught is going to be 0 because my alternative hypothesis is just really hoping that my population mean is greater than 0. And so I choose the mu greater than mu naught option on my calculator. We'll make the color... If you make the color white, I wonder if you see it. Let's try it, I guess. Calculate or draw. Okay, so the answer is no, you don't see it if you choose white. Not the most groundbreaking feature. And notice that this time, again, the shaded region represents the probability that you're wrong. So my p-value is 0.59. And if my p-value is 0.59, that means there's a 59% chance that this pill does nothing. And the amount of confidence you should have is less than half. And it's maybe a little bit important to talk about. It's that we've really found no evidence whatsoever that this works. So the 41% confidence here, that doesn't mean like, oh yeah, like maybe it works. Like, 41% chance, that's like a 2 out of 5 probability that this is going to do something for me. I would tend to disagree with that interpretation, just because, again, in your data that we collected, it showed that people were actually having worse pain if they took the gout treatment pill on average, right? I mean, that really represents no confidence. So my point in showing you this example is that if your confidence is less than 50%, or if the probability of a type 1 error is greater than 59%, then you have no trust.